thumbs up. What's making incredible? What's making it not so incredible? Exams. Okay. What's that? Okay. All right. I've been doing some thinking and talking with you. We're going to change the format for the class for the last 6 sessions. Okay. So what's going to happen is we're going to get to have a kind of more standard lecture. All right, and that'll be what we do. With some pauses, we're going to work on problems. The positive thing is I also extended the time for when you can turn in your attendance, so that happens. So you have 10 minutes extra at the end of class. And maybe something that will be a little bit harsh, but we're going to do it so that we're focusing on the content of the class that we're covering together. The assignments will now be due at the beginning of class. Okay, so this one will be due, the one that's assigned today will be due before we start on Tuesday. Okay? Yeah, you can actually, yeah, so that we're focusing on the current content that we're doing and that it's done, right? So, all right, let's get started. Today we are covering a classic topic that kind of is a rite of passage for mechanical and civil engineers, and it is called Mohr's circle. Okay? Now, this is our 3rd time talking about stress in 2D. Okay? The first time we talked about it, we introduced the idea of equilibrium on a triangle. Then we talked about how to go about doing a general formulation of that, such that it is going to be using stress transformation equations. And last time we used the stress transformation equations to be able to figure out when you have principal stresses and when you have maximum in-plane shear stress. Today, what we're going to be doing is introducing a graphical method that will allow us to do the things we did before. Yes?
I raised my hand before you start talking. What's the last session that's going to be on the next exam?
I think it's 20. All right, it's the penultimate one. All right, the one that's 2 before the day of the exam.
So next Tuesday.
Yes.
Perfect time.
So this is the penultimate. Penultimate cover.
No. We have, so second to last, right? So this coming Tuesday, yes, will be the last one that we cover that's on exam, right? Then we have Thursday session, right, that's not on the exam, right? Does that make sense? Okay, here we go. So, Mohr's circle, we're going to go over its derivation, okay? How you go about taking what we've been talking about with the geometric transformations, or with the algebraic transformations that we have, or trigonometric, if you like, and thinking about how we can go about using another graphical technique. And then we'll also talk about how we go about constructing Mohr's circle, okay? And for this, there are some nuances. It's a little bit complicated, but once you've got the hang of it, it makes you never ever want to do the equilibrium on a triangle again, and hopefully not use the simple but somewhat long equations. All right. And then finally today we'll cover what and how you use Mohr's circle with structures. Okay, so a simple kind of example that goes back to what we've been talking about with things that we've been looking at in the past, like pressure vessels or a rod under tension or a beam. Okay, so this is a slide that goes back to session 17, and just to remind us of some conventions. So what do we see here? We see a few different things, right? One, we see that this is a 2D element, all right, that we like. Okay, and we see that we have some normal stresses here, and we have shear stress. Okay, and this is drawn such that everything, all these stresses you see are positive. Okay, so the normal stresses coming out of the element are positive, and the shear stress where x is coming out of this space, right, and y is up, right. This is the one on the right is the one I typically look at, okay, because this, as you recall from the subscripts, right, the first subscript is the x phase, the second subscript is going to be the direction. So this is in the positive y direction on the positive x phase. Okay, and we talked about how to do the cuts, right? And the cuts are maybe a little bit counterintuitive, but I highly suggest that we use very acute triangles when doing these cuts, right? And this data that you see for the angle of rotation is the same as this data that you see here, right? And then you expose the face, and we can do equilibrium like you see here. Okay, this is the generalized result, right? If you're not using numbers and you're doing all the trigonometry correctly, and then you do some simplifications, right? We can figure out for a given set of stresses, sigma x, sigma y, tau xy, and an angle, we can figure out what the new sigma x prime is going to be, and we can figure out what the new sigma y prime is going to be, and we can figure out what the new tau x prime y prime is going to be. Session 17. And this is from session 18, right? What we said is we could take the derivative of these expressions, okay, with respect to what? With respect to the angle of rotation, set it equal to 0, and then figure out where we have maximums or minimas. Maximas or minimas, okay? And this was useful for being able to calculate out the maximum in-plane shear stress, as well as figuring out the principal stresses. Okay. So, what's next? What's next? Mohr circle. It looks complicated. All right. You're like, what in the world is this? Okay. Well, we're going to go through what Christian Otto Mohr presented. Okay, in 1882, and the idea is that it's a tool that allows us to visualize what's happening with the transformations using a circle, okay? And you're like, oh, that kind of makes sense, right? We're using trigonometric functions, and if we go back to how do we define trigonometric functions? Define them with a unit circle, right? This circle is not going to have radius 1, I think in almost all cases. All right, but that radius will be tied to the state of stress, okay? Its location will be tied to, its center is going to be tied to the normal stresses that you have, okay? And don't worry, we're going to go through this very nicely and I hope it will be nice, and I hope it will be pretty gentle, okay? But this is just to give you the overview. But what we're doing is we're going from this type of state of stress for a general element, we're rotating the element, and then Mohr circle helps us figure out what the new state of stress would be for that rotated element. So, let's do some derivations. All right, we start with some equations that we had for calculating out sigma x prime and tau x prime y prime. Okay? These equations, right, come from the equilibrium on the triangle, and they are the general formula. So this is nothing new. Okay? What we're going to do is rearrange sigma x prime, okay, as follows, right? Nothing crazy at this point. Okay, what you see here is that this side, this has been moved over here, right? And the right side now just has everything that you see on the over here. Okay, nothing crazy. Then what we're going to do is we're going to square these expressions, okay, and add them together. So we're taking this expression right here, both sides, and we're squaring both sides of it, and we're taking this expression right here. Whoops, you can't see. Sorry, I was pointing at the wrong thing. We're taking this expression right here, squaring both sides of it. We're taking this expression right here, and we're squaring both sides of it. And what do you get? This thing. Okay? All right, so this is you're like, this is supposed to make our lives easier. This is not looking like it's making our lives easier, is it? Okay. Hold on. We're gonna get there. All right? We do a little bit of trigonometry or algebra, okay? And the next thing that we get is this expression. Okay? Now, what do you see here? You see something squared plus something squared equals something squared plus something squared. Okay, so you're like, that's not really that interesting. Okay. Does anybody remember the equation for a circle back in your pre-calculus days? What is it? Someone tell me, what's the equation for a circle? Yes, Paul. Yes, that's exactly it, right? That's the equation for a circle. We have something minus something squared plus something squared equals something that we can take the square root of. Okay? So what's going on here? What's going on? Well, we're going to say that we have one axis, all right, that we're going to just define as a sigma. This is the axis for normal stresses. Okay? And then we're going to define another axis, a y-axis, in terms of shear stress. Okay? So we're going to have a horizontal axis that's got sigmas and a y-axis that has taus. Okay? And remember, you were saying x minus x naught squared, right, for your equation for a circle? Guess what? This right here, that's the offset from the origin, right here. This, and what is this? This sigma x plus sigma y over 2? That's nothing more than the average of the normal stresses. Okay? So this right here is going to define where the center of the circle is, that x naught. Over here, we actually don't have a y naught. Like I think Paul said, y minus y naught squared, right? The y naught is just going to be 0. Okay? So this circle is always going to be on the horizontal axis. Okay? But where it is on the horizontal axis is determined by the average of the normal stresses. Okay? Again, we'll explain this in more detail. Okay? This is the radius. Okay? The radius of the circle, right? Or the square of the radius. Okay, on the right side. Okay? And so the format that we're looking at is something like this, right? This is Paul's x minus x naught squared plus a y minus y naught, which the y naught happens to be 0, and this is equal to r squared. Okay? So this is the form of a circle. And, well, we already said this. The center of the circle is that sigma average, okay? 0. Okay. Now, this is what Mohr circle looks like. Remember we were just talking about this? Again, we're going to go through this slowly, all right? But look, there's the center, all right? The C, we're going to say that's the center of the Mohr circle. You see this? This is the sigma. That's the x-axis. Right? So we don't put x there, right? X has another meaning. X refers back to the material element, right? In the direction of the material element. Y also refers back to that, okay? In Mohr's circle world, we have a horizontal axis that's a sigma, and we have a tau, okay? Now, this is the peculiar thing. Tau positive is down. Yeah, that's annoying, right? So tau positive is down. We will talk about why this is, okay, in a little bit. But when you draw this, tau is going down. Okay? And then if you use Juvenile's book for DMC next semester, tau goes up. So, but it's because it doesn't make a big difference with the magnitudes of the stresses, but what it does do is it messes with their head in terms of the orientation, the direction of rotation. Okay, and we'll go through this in a minute. So at this point, what we've said is we have an equation of a circle. Okay? And we've said that we have a radius, okay, which is defined by that big monstrous thing, square rooted. I don't know if you can say that. Can you say something is square rooted? Probably not. The square root of that thing, all right, on the right. And the center of the circle, all right, that x naught is going to be defined by the average of the normal stresses. Right, so if we take it back here, if I give you an element, all right, that has a sigma x, sigma y, tau xy, right, you can plug and shove if you want, right? What's the center? Boom, average, all right? What's the radius? Well, it's this, actually, it's this thing right here, this big, nasty expression. So you can figure out, if you want, using these equations directly to, again, draw more circles. Is that how I suggest you do it? Well, with the exception of, you definitely want to calculate the average to find the center. Actually, it's not bad. It's not bad. It's not bad. We'll talk about how to kind of maybe think about calculating this radius a little bit differently than just using this equation, using a little bit of geometry. But it's not a bad approach. Okay, and if you get stuck, you can go back to this. And again, the center of the circle is at sigma average, comma 0. Okay? Now, we just went through all this. What in the world? All right? So, center of circle is at sigma average 0. Okay? And in this class, we're going to use a convention, another convention, okay, of positive tau, as we were saying, going down. All right? So we're using number 2 over here. Okay? Different books can use different conventions. Okay? That's okay. Different classes can use different conventions. There are reasons for using different conventions. Right? The reason we use this convention, okay, is because we haven't covered this so much yet. You see this theta? Remember this theta? Remember that theta? That's the theta, right, corresponding to how much you're rotating your elements. Which direction? Is that counterclockwise or clockwise? Folks? Counterclockwise or clockwise? Theta, the way we've been defining it. Someone? Anyone? Huh? Yeah, it's counterclockwise, okay, right? Now, with Mohr's circle, if you define it this way and you use our current conventions for what is positive, okay, if we put the tau in, a counterclockwise rotation of the element corresponds to counterclockwise rotation on Mohr's circle. Okay? So that's why we use this convention with our other conventions. It's like we've stacked up conventions and we're going to agree on this. Note, we will all make this mistake. I will make this mistake again in my life. The rotation on Mohr's circle is 2 theta. The rotation of the element is theta. Okay? So if we rotate an element 45 degrees, that corresponds to a rotation on Mohr's circle of 90 degrees. If we rotate an element 90 degrees, it corresponds to a rotation on Mohr's circle of 180 degrees. Great. Okay, so what I want you to do now, please, we're going to do just 5 minutes, okay? Work on question number 1. Just do it, knock it out. All right? Yes? Yes. I'm sorry, say that, Paul? Okay, so this cool figure, all right, is saying that you can have different types of conventions for the state of stress. So first, these two, okay, so all three conventions use positive normal stresses coming out of the face, right? So it's like, that we all agree that that's gonna be positive. That's nice. Then, if you come over here, you see this, then we're saying that this is positive, okay? They're saying in this convention number 3, that would be a negative stress, okay? So we said, okay, we agreed on this as being positive, then we also agree that we're gonna say this right one is positive, okay? And then we come over here and we have a choice. Do we do tau positive going up or tau positive going down? And we made that choice too. We say tau is going to be positive going down. Therefore, the rotation of our Mohr circle matches the rotation on the element. Right? But if you decided that you wanted to do it upward with this convention, then the rotation is opposite. If you decided that you wanted this tau to be negative, then you go down to convention number 3. That's all this is saying. And if you really wanted to, you could do all the trigonometry to like get to this. This is just a nice figure that explains the decision-making process for our convention. Okay? Great. So spend a few minutes working on question number 1. All right? And then we'll go on. All right? But if you have questions on this, we can pause this here on here for just a few minutes. All right? I just want to get your appetite whetted. All right? For what you're doing on the homework. So you still have a little bit of time to do this. Yes, Matt. Yeah. We haven't explained the power of Mohr yet. Okay, we will. This will make your life easier. You'll be able to look at a state of stress for all Mohr circle and be like, damn. I know the power of Mohr circle is in maximum injury, shear stress, and you talk about that is the power of Mohr circle. Okay, so for question number 1, right, what we have here is a sigma x, a sigma y, all right, a tau xy, okay, and it's asking what are the coordinates for the center of Mohr circle, right? So question number 1, or sub-question 1, for calculating the center of Mohr circle, what's the second component? If I'm thinking in terms of sigma comma tau, the center of Mohr circle is going to be tau equal to 0, okay, right? It's on the horizontal axis. When we have the sigma tau coordinate system now, and the second component is 0, all right? So, what's the first component? What's the sigma component? Right, it's just the average of these, right? It's just the average. Does tau xy come in dictating where the center is? Do I care about tau xy for calculating the center of the Mohr circle? No. Okay. So this is a pretty straightforward problem, right? So essentially, what's the average of 150 or 150? The average is 75, right? So you got your first one knocked out. Any questions on this? Any questions? No. All right, we're going to move on. And hopefully you just got a couple points, or got a point. Okay, part 2. we're going to now talk about how to construct Mohr's circle. It looks like a lot. Okay, right? You're like, whoa, I've got angles, I've got my really bad drawings, I've got P and P naught, and all kinds of crazy stuff, okay? It's not that bad if we do it step by step. And here are kind of some of the steps, okay? So the first thing is we're going to want to draw the axes, okay, with sigma on the horizontal axis, okay, and positive tau going downward. So what does that look like? Real interesting, okay? Draw it like this, okay? Now, if you draw it like this, all right, that's suggesting that the center of Mohr's circle is going to be positive. All right, so that's usually not a bad way to go. All right, we tend to do more problems where you have things in tension. Okay, so but if you're not sure, like, do I need to draw more over here or more over here? Calculate the average. Right, calculate the average of sigma x and y, sigma y, right, and then you'll know where that's going to be, where it's going to be centered. Okay, but I'm getting ahead of ourselves. Right, because the next step is to plot the center of the circle, okay? And how do we do that? Well, we have the formula, right? Sigma average is equal to sigma x plus sigma y over 2. And then we say, all right, well, I can write out its distance to the origin as such, okay? So far, pretty simple, right? I know where the center of the circle is. Now, this is where maybe it gets a little bit interesting compared to what we talked about, because we want to draw a circle. So you could go ahead and draw a circle based on the r squared equals that nasty square root of the difference, the square root of 2 plus the tau y squared. All that, you could do that. But we're going to suggest that you actually plot a reference point. Wait, what? Okay. This is where it starts to have some meaning. Typically, you're going to want to pick sigma x and tau xy. And then you're going to plot that point right there. Okay. So, sigma x, all right, is just the horizontal distance, right, to this point. In some respects, you don't even have to think about where the center is, okay? But we are going to draw a line between them in a minute, okay? And what is tau xy? Tau xy is how far down you are. If tau xy is positive, right, this is where I would make a mistake, you make a mistake, we all make mistakes. If tau xy is positive, it goes underneath. Because tau xy, or tau, the tau axis is positive in the downward direction. Now, remember how I said you could use that equation to figure out the length of radius r, okay, or figure out radius r, sorry. But it turns out, okay, one of the reasons we're using this, that this point P is on Mohr's circle. Okay? So point P is on Mohr's circle, which means that if I know the distance between the center and R, or the center and P, C and P, I can figure out what the radius is. Okay? So you tell me, what are the different ways to figure out this length? Yes, Zach. Okay, you could use the distance formula. Okay, you could, right? What's the distance formula? Distance is equal to the square root of sigma x minus blah, or sigma x, or not sigma, x1 minus x2 squared plus y1 minus y2 squared. You could do that. You could use the distance formula. How about another way? I want a trigonometric way to do it. How do I do it? Think high school geometry, or middle school geometry for some of you. Okay, it's not even really, it's geometry, it's not really trigonometry in this case. How do I figure out the distance between C and P? Come on, guys. Yes, Malaya. Come on. That would be the Pythagorean theorem, wouldn't it? Yes, that's all it is. All right? Look, I can figure out what this distance is. It's sigma x minus sigma average, right? That's this distance. And I know what tau xy is. That's the vertical, right? So this distance is just going to be that your r squared is equal to this squared plus this squared. Okay? Geometry. We're doing it. Okay, so we figure out what that distance is, right? Which turns out to be sigma x minus sigma y over 2. Okay, why? Because sigma x minus that is going to give us this. Okay? And yeah, so you could write this formula down, or you could look at it every time, which is kind of what I do. I look at it every time, like, oh, how do I figure that out again? Right? And then I figure out what this distance is, and I figure out what this distance is. Okay, that tells me what r is going to be equal to. And this is the same big bad equation that I didn't want to remember. Okay, but you probably should write on your formula sheet just in case. Okay, now we figured out the radius. Okay, we figured out the radius. What is going on? I've now done something very interesting. I just drew something, a 2 theta. Okay? And we're going to get back to how to use this in a little bit. Okay? Well, I'll just tell you how we use it right now. If I want to rotate my element by theta, let's say I want to rotate it 45 degrees. Okay? What I can do, and this is where Mohr's circle becomes very powerful, I can say, oh, my element's rotating 45 degrees. 2 theta is going to be 90 degrees. I can rotate 90 degrees on Mohr's circle. Let's say it's about here. Okay? We're right about there. And then we can figure out what the new state of stress is. That new location will describe a sigma x prime and a tau x prime y prime. And that is the power of Mohr's circle, or part of the power of Mohr's circle. Okay. So, what can we do? One, like I just said, we can find stresses in an arbitrary orientation. When I say arbitrary orientation, really we're only talking about rotation about the z-axis. Okay? So it's not super arbitrary, right? But if you give me a theta, I can use Mohr's circle to figure out what the new state of stress is at that location. We can, once again, plot everything out, okay? And what we're saying now is if we go to a new location, that new location that we've rotated now 2 theta on Mohr's circle is the sigma x prime tau x prime y prime. Okay, any questions on this? This is pretty critical to why we're doing Mohr's circle. Okay? So, do we ever get off of Mohr's circle for our problems? No, not always are in plane. Okay, we do some stuff we do 3D that will be a little bit off, right? But if you're looking at the in-plane state of stress, stay on Mohr's circle. Okay. Now, here's something that's a little bit wild. I didn't talk about sigma y, all right, previously. Okay. Sigma y, I probably should have drawn it out, but if I went like this, if I went out to here, whoops, 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 okay, like that, this would actually be, whoops, okay. This is, this will probably be more clear, okay, in a little bit. But what I'm trying, I lost my mouse. Okay. What we're trying to say here is that I can plot point P, which is sigma x comma tau xy. I can rotate over and plot a sigma x prime tau x prime y prime. But if I want my sigma y prime, I have to go to this part of the Mohr circle. Now, why is that? See, let's think about that. Why is the sigma y or sigma y prime on the other side of the Mohr circle from where sigma x is, or sigma x prime is? Any ideas? Why would it be on the other side of the Mohr circle? What do you all think? Why would it be there? Yes. Okay, yes, okay, yes. So we can use, because we plot the geometric transformations, we know that, yes, there are these sinusoidal patterns, right? And so one goes up, the other one's going to change, go the opposite direction. So good, right? Because as this is going up, right, if P is going up, then across here, this is going down. So that models that. Why directly across? Yes, Michael.
I know you mentioned
Correct. Okay. What is the angle between x and y? Or x prime and y prime? It's always 90 degrees, right? So we did this problem in the past, right, where we rotated like 90 degrees, right? And then everything just flips, but the state of stress stays the same. If I rotate x 90 degrees, that is going to be where the y was, okay? And theta, 90 degrees, right? On Mohr's circle, 2 theta, right? That would be 180 degrees. So these 2 points are 180 degrees out of phase with each other. Excellent. Okay, so one thing that is really cool, now this is where we get to the power. We can find principal stresses super easy. What is the definition of a principal? What do we know about the state of principal stresses? Just recall. We've now done this. Yeah, Paul, you're raising your hand attentively. So what do you think? What do we know about the state of principal stresses? Shear is 0. When is shear 0 here on Mohr circle? Yeah, on the sigma axis, right? So guess what? If I'm interested in going and finding the principal stresses, all I've got to do is move to this location and that location. That's when I'm going to be on the sigma axis, or when tau is going to be equal to 0. Okay? So what we do, remember, we have a sigma 1 and a sigma 2. Okay? Typically, we say sigma 1 is larger than sigma 2. All right? That's another kind of sort of rule. So we just look over here and figure out where sigma 1 and sigma 2 are located. Now, what is sigma 1 equal to? Using geometry again. Using geometry, what is sigma 1 equal to on this? Yes. Very close, not quite. All right. I agree that sigma 1 minus sigma 2 is the diameter, or 2r. Okay. Oh,
is it the total length?
Okay, how would you define that? Can you tell me what you mean by total length?
Would it be the diameter plus the distance from the origin to zero?
Okay, yeah. So it's the radius, right? So if I'm figuring out sigma 1, right? It's the center location plus the radius. And the center location minus radius. So remember, center is the average of sigma x and sigma y. And actually that center is the average of any sigma x and sigma y. So sigma x prime, sigma y prime, I add them and divide by 2. That's where the center of Mohr's circle is. Okay? So the center is not changing unless the state of stress changes. Meaning like the load increases or something like, something changes. But what you're seeing here, okay, is that I can very quickly figure out where sigma 1 and sigma 2 are. Okay? No more set the derivative of the geometric equations, figure out what that solution is, plug into the formulas. I look at Mohr's circle and I say, I know where the center is, I know where the radius is, I know what the radius is. Boom, I can figure out sigma 1 and sigma 2. Okay? So if that's powerful for calculating out the principal stresses, what do you think I'm going to talk about next? What's the other thing we often care about? Yes. Yeah, so the maximum in-plane shear stress. And where is that going to be?
I guess like the power coordinate would just be radius.
Yes. Yes. And on Mohr's circle, like I agree it is the radius. Okay, and on Mohr's circle, where should we find maximum in-plane shear stress?
Sigma coordinate would be at the center.
Yeah, so it's going to be at the bottom and the top. Okay, right? Because this is going to be tau xy, and the top one would be negative tau xy. Okay. So once again, it can be very useful to figure out what this quantity is just using geometry. And as Zach said, it's just the radius. It's just the radius. It's not the diameter, but it's the radius. Okay, and we calculated the radius right earlier using the Pythagorean theorem. Any questions at this point? Okay, this is why Mohr's circle is so powerful, because it tells us a way, it gives us a way to figure out a state of stress for the given rotation using geometry. But boom, it tells you, uh-oh, what did I just do? Oh no. Oh no. Does anyone know how to shut that off? Someone want to do a quick Google search on how to eliminate the voice? I don't kind of like that. Wow. It's pretty good though, isn't it?
It is.
You like it? All right, well, I don't know how to start it again, but we'll let it keep going just for kids. Okay, how do I do that?
It should say captions on the either bottom or top of the page and around the
Okay. Okay. It was actually something called toggle subtitles, but very good. Subtitles. Okay, so that was exciting. All right, so here's an example. If we have an element, the same state of stress we were just talking about, right? Where we have sigma x equals 100 megapascals, okay? And sigma y equals 50 megapascals, and tau xy equals 10 megapascals, okay? And we rotate the element 30 degrees counterclockwise. What are the resulting sigma x prime, sigma y prime, and tau x prime y? Okay. So yes, you could just, this is what you probably say, I'm just going to use my equations. Alright, yeah, okay, fine. But what I'm trying to show here is that no, we can use more circle to do this. Okay. So what do? We draw the axes, okay? We plot the center. Okay. We then put our reference point down, okay? What is our reference point? Well, it is sigma x, tau xy. So sigma x is 100 megapascals. Tau xy is 10 megapascals. So we put this down, and then we know that it's here. All right, we already kind of drew that. We figure out the length of the radius r, and how do we do that? By using Pythagorean theorem, right? Because we can figure out, oh, this is going to be sigma x, or this distance right here is the sigma x minus this the average, and then we have tau xy, right? And that gives us our two sides of the triangle, and the hypotenuse is just going to be the square root of the sum of those squared. From there, okay, we got to rotate by 2 theta. Okay, so 2 theta, all right, is going to be 60. So this is supposed to kind of be something close to 60 degrees of rotation. And once we've rotated 60 degrees, okay, we got to figure out what the value is there, all right? So first, okay, what amount, okay, of rotation does it take to get to this nice horizontal? Well, how do you figure that out? You can use trigonometry here, right? And you know that this length is 25, okay? And we know that this length is 10. So the phi, we're calling it, to get to horizontal, okay, is going to be the arctangent of 10 over 25. So that tells us how many degrees we have to go here. So that's 21.8 degrees. And how many more degrees do we have to go? Well, we have to go to 60, right? We have to go 60 degrees. So 60 minus 21.8 is about 38.2 or something like that. Did I do it right? Okay. So we're going to use the 2 theta, okay, and then we go 38.2 degrees up. So now we have this, and this helps us with another right triangle. What do we know? If we got to figure out sigma x prime and tau x prime y prime, we know the angle in here, and we know the radius, right? What is sigma x prime? Sigma x prime is going to be, right, this radius times the cosine of gamma. And sigma y prime, or tau x prime y prime, sorry, is going to be the radius times the sine of gamma. Okay? So now we can figure out where we are. Okay? So we do our cosine gamma, all right? And we can, or you can figure it out this way if you like. Okay? And then you figure out where tau x prime y prime is. Yeah. Any questions on this? Any questions? I gotta be careful what I say. Yes, it's r cosine gamma, right? That tells us this distance, but I should have mentioned that we also have to add to this distance to figure out what sigma x prime is. Yes, Kevin.
In the context of a physical system, what does R mean? So, like, tau is the shear stress, or the in-plane shear stress, and sigma x is stress index.
Yeah. So what is R? What does it really mean? Well, R really is the maximum in-plane shear stress. Right? That's what R is, because remember how we talked about that? R down, if you're down here, right? That's where you have maximum in-plane shear stress. And that tau is corresponding to that. Okay?
Oh, okay. So
right? So that's going to be the max. So that's what R is kind of in a physical sense. It's the maximum in-plane shear stress.
okay.
Okay.
But in the context of just for the purposes of finding what sigma x and tau x y are, that's what it's used for with this relational.
That's right.
Yeah.
That's right. Okay, good. Okay. So that's how you figure out where sigma x prime and tau x prime y prime are. And once again, if you needed to figure out where the tau or the sigma y prime is, okay, you would go 180 degrees, okay, to get to this one. Any questions? I see some people that are just jovial and doing other things. I see some people who have a slight look of perplexion. Okay, questions on this? It's a lot to digest, right? And it is. Mohr circle is a lot to digest. Okay. All right. So, what about in-plane principal stresses? Okay. Well, here's the same thing that we just had. Same exact state of stress. But now we want the principal stresses and the relative orientation. Well, where do we say the principal stresses are? Principal stresses are here and here, right? So this goes to, we can calculate out, we just said it a moment ago, if I know the radius and I know where the center is, right, I can calculate where the sigma 1 is going to be. And sigma 2, where's sigma 2 going to be? If sigma 1 is the center, the average plus the radius, that's sigma 1. What is sigma 2? Yeah, the average minus the radius. Okay, that will give you sigma 2. Good. Okay, so we can figure out the what I like Mohr circle to calculate the magnitudes. It's also useful for calculating out how much angular rotation we have to have. Okay, so last time, remember we said we were 21.8 degrees from the horizontal. Okay, we calculated that by the arc tangent of 10 over 25. Well, that's how many degrees we are away from the state of principal stress on Mohr circle. To figure it out with the on an element, we have to divide that by 2. Because there's a factor of 2 between the rotation of an element and the rotation of Mohr circle. Okay. So that's the rotation, and then as we discussed a minute ago, verbally, we can figure out what sigma 1 is by doing sigma average plus r, and we can figure out what sigma 2 is by the average minus r. Okay. The next example, if we did arbitrary orientation and we did principal stresses, what are we going to do next? Maximum in-plane shear stress. Oh yeah. Okay. So for maximum in-plane shear stress, we have the same state of stress we had to start with. 100 megapascals, 50 megapascals. Okay. And actually, I should delete this because we're not rotating the element. We're wanting to know, okay, what the maximum in-plane shear stress and relative orientation are. Okay, so typo on my part. So what do we do there? Well, we are going to figure out how much we have to rotate to get to the top and the bottom. Okay? And so we think, oh, I've got to rotate some amount, and this would be a clockwise rotation. Okay? This would be a clockwise rotation to get to this state, or you could go around more to rotate counterclockwise, right? And that would give you something that is going to be larger, right? But we know that this angle plus that angle is going to be 180 degrees. Okay, so these are essentially, these states of stress would be 90 degrees of the element relative to each other. Okay, so what do? We say, okay, we're down there, we're up there, that's where we have Q and Q prime. and we can figure out what we already know the sigma average, and we know tau max is just going to be the radius, okay, which we have right there. And if we want the angle, oh, I didn't say the relative orientation. Well, if we want the angle, this was 21.8 degrees, okay, here, which means that this was 38.2, okay, that we had to rotate there. So 38.2 degrees divided by 2 is 19.1. Okay, so we'd have to rotate minus 19.1 degrees on the element to get to the state of maximum inclined shear stress. Okay, we talked about this a little bit already, but if you rotate 90 degrees on Mohr's circle, okay, you're going to get 180 degrees, okay, if you rotate an element 90 degrees, you're going to get 180 degrees rotation on Mohr's circle. This is showing 90 degree rotation with the element, right? So sigma x comes up to the top, sigma y comes over here, like you see here. And we can say, okay, sigma x prime is equal to the original sigma y prime is equal to the original sigma x, and the tau x prime y prime is equal to the minus tau x y. Because if we look at what's happening here, this is the x face, right? And is this going to be in the positive or the y prime direction?
Yeah.
It's in the negative y prime direction. So it ends up being a negative graph. Okay. On Mohr's circle, we can see this without too much difficulty. We have our initial state of stress. We're some location. We rotate 180 degrees on Mohr's circle to get to this location up here. Okay. And that corresponds to the 90-degree rotation of an element, and we have what we have there. Okay. Good. Okay, go ahead. Now you've got a few questions to help reinforce this. We'll give it a few minutes for you to work on this. Okay. So question 2 says you've got a state of stress. All right. Use Mohr's circle to determine the larger in-plane principal stress. Okay. Question 3 is asking what is the angle rotation to get to the state of principal stress, and as you might guess, this next question is what is the max in-plane shear stress, and then the next question is what is the amount of rotation that you need to get to this max in-plane shear stress. So go ahead, spend a few minutes on this, all right, and then we'll go on to the final topic. Yes.
Can I ask a question?
About what? On this? Yes. This is what we're talking about.
No, I mean,
About what?
it's about
Which problem?
unrelated.
Well, I'd rather take questions related to this for now. Okay? All right, so start with this one, right? Okay. How are we going to go about calculating the in-plane principal stress, the larger one? What is your procedure? What is your procedure? How do you go about it? Just in words. Before you do this, how do you approach this? so you gotta calculate the radius, right? Yeah, okay. So go ahead and spend a few minutes drawing it out, okay? Yes, that was a great verbalization. There's one tricky thing here. What is the tricky thing what do you think is the little tricky symbol I put in? What do you think I put in that little tricky? Yeah, we have a negative shear stress, right? So where does that go? If you're gonna look at the circle, does it go above? Yeah, it's gonna go above the horizontal axis. Yeah, good. Good. Okay. Other thoughts on this? Alright, so that's kind of the general procedure. Right? Figure out where the center of Mohr circle is based on averages, right? Then plot the point sigma x tau x y, right? Sigma x tau x y. And then and that's going to be, in this case, it's going to be up to the right. Okay? It's going to be, because that tau x y is negative, so it's above the sigma axis. And then you can figure out, using the Pythagorean theorem, right? You can figure out what the radius is. And from there, okay, once you know the radius, then as Zach pointed out, it's just the larger one is the one that's further on the right. Okay, over here. All right. You're going to be looking at this type of system, right? This is the sigma axis, this is the cos of tau. This is, let's say this is the center, right? That center is at the average of these. Okay? In this case, okay, we have our sigma x tau xy up here because this is negative. Okay? Because that's negative. And then we're interested in figuring out what this point is right there. That's where sigma 1 is going to be. And that sigma 1 is equal to the sigma average plus r. How do you figure out r? You figure out r using, if you want, x, y. That's probably not the best. Let's do it this way. What is A, B, C, right? R is just C in this case, or I can just use R, whatever. Let's just use R, I guess. So R is going to be equal to the square root of A squared plus B squared. And in this case, B squared is just tau, or B is just tau xy. Okay. Like that. Okay. So that's how you go about doing that one. Maximum in-plane shear stress. How are you going to tackle this one? Someone else? Anyone? Just in words. Yes?
Find R when there's a 90-degree, like it's straight down.
Yeah.
Find the magnitude of R.
Yeah. So pretty much, right, this is the same state of stress that we just had initially. And we already went through the painstaking effort of calculating out what R was. So we know what R is going to be, right? So we're, in this case, okay, we were here, okay? Right? And we know that this is R, okay? Now we need to know the angle of rotation. So that's kind of a pain, all right? It is, okay? So what is the angle of rotation to get to a transform state in principal stress? Well, if I want to make it less than 90 degrees, that means I'm going to try to rotate up to here. Okay, I'm going to then move, because this is going to be, right? That's where I'm going to be talking about, and this is going to be my tau max is up here. It's actually negative. Okay, but to figure that out, I need to know, okay, what is my original angle, my phi, right? And my phi in this case is going to be the arctangent, okay, of the tau xy that I had, okay, or the magnitude of the tau xy, probably safer to do it that way, over, remember, I've got to figure out, actually, I don't have to do arctangent. I can make it easier. Since I know that, I could say that it's actually the arc sine, okay, right, of the tau x y over r. All right, that makes it a little bit easier. And so I know what that phi is, okay, and then I got to figure out what this is, what that angle is. That angle is going to be 2 theta s, right? So 2 theta s plus the phi is equal to 90 degrees, right? And that will allow me to figure out what theta s is. Okay. Good. Question 4, right, is actually kind of simpler, because question 4 is what is the max? Sorry, I lost my pointer. What is the max in-plane shear stress? And what is that? That's just R. So that one's simple. And then in this case, we already did the angle of rotation. Okay, we already did the angle of rotation. Oh wait, did I make a mistaker? Oh, I made a mistaker. Sorry, I was doing max shear stress. You guys, I was doing maximum shear stress. This one, it's actually, so this is for max shear stress. I made a mistake. Max shear stress. Yeah, but what we actually want is to rotate down to here. Sorry, guys. So I need to take phi divide by 2, and that will give us the angle of rotation. Okay? That we need. So angle of rotation is going to be equal to actually negative phi divided by 2, because I've got to rotate clockwise instead of counterclockwise. Okay? All right. Let's go on to part 3. We're almost there. Okay? So we've done a lot of talking about elements. Okay? But these elements are just somewhere in space. And nothing is going, right? Let's attach these elements to a structure or structures, right? So that's what we're going to talk about now. We're going to talk about how to use these with structures. Okay? And this is not, probably, you all are probably like, this is pretty straightforward, right? If I can do all this, and then I just got to figure out with my combined loading experience what the state of stress is, then I can figure out what's going on with having to do the transformation. Okay. So, we've already kind of talked about this. Let's first start with uniaxial loading. What does uniaxial loading look like? It looks like a bar under tension, okay? And it has some cross-sectional area. The stress, if we go way back, how would you describe the state of stress here? Anyone? Yes, Paul. Yeah, P over A. Now, what are the other components of stress? 0, right? So I've got one component of P over A, I've got another normal component of 0, and I've got shear stress of 0 in this case, right? This actually sounds like a state of principal stresses, right? Because I've got no shear stress. So I can actually go ahead and write that the larger of the principal stresses is just P over A. Okay. And sigma 2 and sigma 3, all right, which would be the third principal stress, which we'll get to in a little bit. Okay, but those are also 0, as is tau xy. So the element looks like this. That's it. And I could have decided that I wanted to do sigma 1 coming out the top or the bottom, but I just decided that I'm going to do it in horizontal direction. Okay. So from here, we add our coordinate system. And what does the Mohr circle look like? Okay, guys, what's the Mohr circle look like for the state of stress? It's going to be plastic. It's going to be, this is something you might write down on a napkin to impress your boss someday. Actually, probably not, but maybe. Let's be optimistic, right? What does Mohr circle look like here? Someone else, because you're on fire. Someone else, come on. What does Mohr circle look like here? Yes. Okay. There is a trick question that you'll see that I do sometimes, where the Mohr circle is a point. Okay, but it's not going to be a. I would say, okay, Mohr circle. It needs to be a circle, right? But what is that line? I think let's take what you're saying. What does the line look like?
There's no shear stress.
There's no shear stress, right? So we've got a point, right? We're on one side, and then what are the other two? What's the other point? Where's the other point? I got one point that I'll say has some value, right? On the x-axis. That would be sigma 1, right? That's P over A. Where's the quote sigma 1? No, so sigma y, what is sigma y here? It's 0, right? So where is it on the sigma tau axes? Well, where can I have 0? Yeah, at the origin, right?
Oh, yeah.
At the origin, right? So when you say line, sure, there's a line here, okay? There's going to be a point over here, and there's going to be a point over here. Okay? What were we going to add?
I was just gonna say the one side of the circle at the origin, the right side.
Yeah, okay, and where's the middle? Where's the middle of this circle? Yeah, it's going to be at P over 2A, right? It's the average of sigma x and sigma 1. Okay, so here we go. That's what Mohr's circle looks like. Okay, and that's the sigma 1. Sigma 2 is right there. And you can say that the middle is just sigma 1 over 2. Okay? So, this is a biggie. What is tau max? Or tau max better down here. Okay, but what is tau max? I see you think you know it. Come on. What's tau max here? Well, what's the radius of this circle? Tau max. Good. Okay, so tau max is the radius. And what is this point right here? That's sigma 1. It's just the stress, T over A. Right? And what's this point? This one's sigma 1 over 2. So the radius is just sigma 1 over 2. Right? Or this is the center, right? We said was at sigma 1 over 2. So the radius is just sigma 1 over 2, which means that the tau max is also sigma 1. Okay? This is powerful stuff. When we cover criteria for failure, we are going to be interested in materials that fail by maximum normal stress and materials that fail by maximum shear stress. Ductile materials, like most of the steels that we've been talking about in this class, they fail because of maximum shear stress. The brittle materials, they typically fail from maximum normal stress. these transformations allow us to go between maximum principal stresses, at least in a plane, and maximum shear stresses, at least in a plane. So it allows us to figure out if the ductile material has normal loading, what is the equivalent shear stress that we have to be worried about for that ductile material. Okay, we did it. 45 degrees is also the angle rotation, okay, that we had to go. Pure shear is another classic case, and guess what? With pure shear, you can get a state of principal stresses where you have no shear. Okay? This is awesomeness. All right? I'll let you take care of that in a little bit. Okay? For the homework, you will have an opportunity, okay, to think about a spherical pressure vessel. And think about what the state of stress is on a spherical pressure vessel. What did we cover today? We derived Mohr's circle. Woohoo! Okay? This is a big step in your engineering career. All right? You now know what Mohr's circle is. You didn't know, maybe some of you knew what it was before today, but now you definitely know what it is. And then we've talked about how to construct Mohr's circle, and we have connected Mohr's circle to structures. So in this case, we talked about uniaxial loading. We talked about shear very briefly, right? Pure shear, so that's a rotating shaft or a twisted shaft. And then we talked about doing a spherical pressure vessel and a cylindrical pressure vessel. Okay? It's now your favorite part of the time that we have together, okay, where you get to do your attendance. And good. I hope you all have a wonderful weekend. Okay. And if you have questions, please feel free to send me messages over Canvas, and I'll try to get to you. Okay. Thank you for continuing to use the group me. All right. Good stuff after that. Thank you. Yes. Oh, let me stop. Let's see. Stop this thing.